from Yamaguchi University. Yes. Please, you can start.
Okay, hello everyone, and welcome to my presentation. I am AzizulMoqsud. I am Associate Professor in the Department of Civil and Environmental Engineering, Yamaguchi University. So at first, I would like to thank all of you for attending to my presentation. I am very happy to be here today. And today I am going to talk about 1 hour of research in biocementation. So we tried to make our slope harden with the help of bacteria. So you will come to know how this is interesting. So this is the contents of my presentation in general. Today I will talk about some introduction and some background, and I will show some laboratory tests as well as field tests of biocementation, and finally I will conclude. So let's start with the introduction. So look at this graph provided by NASA. It shows the landslide potential. So you can see it is very much susceptible from North America to Asia, all over the world actually. So we saw previous lectures in New Zealand as well. So especially in the main island, southern part of Japan, so it is quite potential for landslide disaster. And most of the protective work are done using the chemical cement, so like concrete and other things, so which is not environment friendly. So our target is, can we make a little bit environment friendly? And because we don't want to use chemical cement much, because one of the major reasons for carbon dioxide emissions, so 8% of the total CO2 is emitted from the cement industry. So we try to learn from the nature. So this is one of my favorite slides in this lecture today. So actually in the nature there are a lot of engineering and we can learn from there. And today's lecture is related to cementation. So in the nature, if you go to sea beach, you can find some like rock-like materials, but basically those are sand and those are binded or made hardened by the bacteria. Okay, the metabolism of bacteria, it becomes like this. So we learn from this nature and try to apply it in our soil mechanics or slope. And this is the mechanism what happened actually. So with the metabolism of urolactic bacteria and with the help of like calcium, they produce the calcium chloride, and which binded the soil particles and make the strength of the soil. But there are some challenges because the cost of the laboratory grade materials and also the risk of biohazards, because you cannot simply bring bacteria from other countries and apply in your field. So the objective of this research is to try to make it our own biocementation in the southern part of Japan with the native bacteria, and also try to reduce the cost of the laboratory grade materials. We try some like commercially available materials to use as nutrient solution. And then we collected our soil slope, natural slope in the Ube city, Yamaguchi prefecture, where our university is there. And we isolated some native bacteria from the slope, and we call it Cytobacillus fornica. And we used some commercially available materials like urea fertilizer and snow melting chemicals, basically calcium chloride, and these are easily available in the supermarket, for example. So by using those materials, we can reduce our cost more than 80% as well. So what we did, we made some like biocemented slope and non-biocemented, we call it blank, and then we tried the penetration strength in different depth. And look at this, this is A, B, C, D. A and C are biocemented and B and D are not biocemented, we call it blank from now on. And A and B are with grass in natural condition, and C and D are without grass. It means we take out all the roots and other systems, so make it like blank condition, and then apply the bacteria and nutrient solution. So this is that just like we apply 10 days of the nutrients, and in the final day some of the grasses dried in the grass area. And for the without grass area, we found some nutrient solution. Or due to the rainfall, the water didn't go inside. So it means that biocementation already started there. And then we check the penetration strength or by the A, B, and C, D, and we found that for the case of biocemented one, it is harder than the non-biocemented, and both for the without grass and with grass showed the same thing, same trend, but without grass showed more like strength compared to with grass, because we applied the nutrient solution on the food for the bacteria from the surface, so it enters properly in the deeper depth without grass. And there was some like big rainfall during that, after that experiment. So continuous 2 days it was a rainfall, and after the rainfall we checked the erosion of that slope. So we took the photos and we did some image analysis, and obviously you can see for the biocementation slope, the surface is much stronger, okay? The erosion was less. On the other hand, the black slope, where there is no biocementation, it has much erosion, okay? This is natural condition, and we did it in the outside of the, in the nature actually we did, and other environmental factors are affecting there, but we can see the difference between these two. Then we checked the scanning electron microscope, and we found that both the A and C, which are biocemented, but this is with grass and without grass. So without grass, the calcium carbonate is much more than the grass one. So maybe we applied in the liquid a nutrient solution from the surface, so some of that is hindered by the grass or leaves of the trees. So we recommend that if you want to do biocement in the nature, so it is better to do with without grass.
Stay 1 minute.
Okay. So then we did some strain test by direct shear test, and we found that both for biocementation one, the strength increased, and if we look at the C and phi compressive strength, and this is also increased with the biocemented one compared to blank sample. So these are the conclusions. So biocementation is possible with the native bacteria and low-cost materials, and then it can be used. So these are the main 4 major problems I am addressing today: the landslide prevention and the high cost of the biocementation, so we can use it low cost, and of course we can use the native bacteria instead of being some foreign bacteria. But most importantly, we can save our earth by protecting the global warming. So thank you so much for your attention. I'd be happy to answer any question you may have.
Okay, any question from the floor? First one, please.
Thank you very much for the great presentation. Have you considered studying the durability and also leaching potentials for the product?
Thank you so much. So actually, this is like chemical cement, so it works for a long time if the calcium carbonate is generated by the bacteria, and if there is no acid rain or acid effect, it will long laster. And so we did it for the small scale slope test, and after 1 year, or we checked the strength again recently, and it was still working perfectly, so no problem with that durability.
Yeah, you can.
I just have one question. The application of the biocement is applied in powder or liquid?
Okay, we applied it in liquid form.
So if it's applied in liquid, I think landslide is a factor of depth and also the infiltration capacity of the soil. So after, let's say, a given period of time, the hardening, have you tried to determine the depth of the effective depth of the biocement?
Yeah. How can it? Okay. So actually, so from this natural condition we check, we only apply the gravitational force, like just apply the liquid, and we found that it works around, I mean, 15 to 20 centimeter from the surface. But if you want to go deeper than that, so in our group, research group, we are conducting using some pipe, okay, and pump, and they apply that in the deeper depth of the liquid, and it works.
I see. So in case of heavy rainfall, like we saw earlier in New Zealand, what is the infiltration capacity?
That is very good question. So actually, it can reduce the permeability of the soil significantly. So we checked in the modern slope test, and we checked the permeability of that, and we found that after the biocementation, the water penetration or percolation is very low. So yeah, it can increase the geotechnical properties and make it like stronger soil.
Okay, so you conclude what kind of soil? What kind of soil you are?
So we actually use in natural slope soil in southern part of Japan. So it is
Sand, silt, or
it's kind of mainly silt and little bit sand is there. Yeah, I mean rain size analysis is like this, but the properties of soil is like we call it granite soil, decomposed granite soil. Yeah,
okay.
the southern part of Japan is made of those type of soil. Yeah.
Okay, thank you. We finished for the second presenter. Give an applause. The third presenter is